Hello, in this video I want to design a roadmap for alkyne reactions. Drawing your own roadmap, maybe based on what you see here, should be helpful in studying synthesis problems. Actually, where I want to start is with an alkyne and show you first all the reactions you could do with an alkyne, and then towards the end of the video I'll show you how to make an alkyne. So that section of the roadmap is actually way down here. And we're starting with this terminal alkyne, and the first reaction that I would teach in using an alkyne is making this alkene halide. What we want to use is one equivalent of HBr. Your professor may or may not put one equivalent. It will just be depending on their preference. And we put a Br on this carbon, the more substituted carbon. We are following actually Markovnikov's rule. And there is going to be in the mechanism a carbocation at the more substituted carbon. Now, if you add another equivalent of HBr, the thing is, the more stable carbocation will still remain at the secondary carbon across from the halide, and you'll put the halide, the second halide, on that same carbon right there. So here we made a dihalide, in this case a dibromide. That's an addition reaction. You've seen addition reactions with alkenes. Now we're just using alkynes, but now we could do the addition reaction twice because we have two pi bonds. What's another addition reaction that you learn in the alkene unit? Br2 or Cl2. Now normally there's a solvent like chloroform. Actually I also want to put one equivalent, and we're going to add two bromines to each of the carbons of the triple bond, and we go from a triple bond to a double bond. The idea here, though, is that from the mechanism, we know that the second bromine comes from the opposite side, so these two bromines have to be trans to each other. So this is a trans dibromide. If we add another equivalent of Br2, let me write it this way. Okay. We add a bromine on each of the carbons of the double bond, and we get a tetrabromide. Down here, tetrabromide. Now, in my textbook, they add a couple more other reagents. I think it's to help make the regioselectivity and the stereoselectivity more pronounced. And those reagents are acetic acid and lithium bromide, a salt. I won't expect my students to write this. If they write Br2, that's good enough for synthesis if you're trying to make the dibromide. What if you want to make the tetrabromide right away? Just say excess Br2, going from alkyne to tetrabromide. Or if you want to make the dihalide right away, just say excess HBr. Okay. Next is an alkylation. And let me put here, let me actually write it sideways. Do you see how we have a terminal alkyne and we added two carbons at the end? This is alkylation. And now we have an internal alkyne. Maybe I could write here also this is a terminal. And this is an internal. Okay. What are the reagents? The reagents are, we want to deprotonate the terminal alkyne using a base, and often it would be NaNH2. And then you have to realize that you are adding two carbons. and the point of attachment is this dot. So you're going to use a primary alkyl halide. There's a dot, and there's a halide. In the mechanism, the carbon anion, the acetylide anion, is commonly known as, attacks this dot, kicks out the bromine. This does have to be a primary or methyl halide, and I'll put that in parentheses. Primary or methyl halide. If it's secondary or tertiary, this substitution, right, alkylation is a type of substitution that would fail and you'd get elimination. I won't go through that in this video. If you want to do this alkylation, make sure you match the alkyl halide and make sure it is primary or a methyl halide. Before we get to these three products down here, okay, let us do two more reactions starting from this terminal alkyne, and they are hydrations. So the first hydration, we are using something that you've seen before, H2O, H2SO4, but this is hydration via a Markovnikov fashion. And also, when you're working with terminal alkynes, sometimes mercury sulfate is added to help, again, accentuate the regioselectivity. Because we are moving, or not moving, we're putting an oxygen on this carbon here, the internal carbon, not the terminal carbon. So we made what's called a ketone. It's a carbonyl group with a carbon on each side. And technically, this mechanism goes through a hydration at the Markovnikov position or in a Markovnikov fashion. So this is, you can think of this as Markovnikov hydration. Now, it may be strange, I thought hydration was adding an OH. Well, in the mechanism, you do add an OH and then it changes to a carbonyl group, but also, look at how many hydrogens you have in the alkyne at this position. You have one hydrogen, but now we have three. So we added two hydrogens and an oxygen. So we did add H2O. Maybe I'll draw the intermediate. How should I draw the intermediate? I'll draw it in, I haven't used color pink yet. I'll draw it in pink. The intermediate is this. Because you do actually add OH in the mechanism, and it looks like that. And then it isomerizes to the more stable ketone. Now, if we wanted to add the double bond oxygen to the N carbon, right there, you would call that non-Markovnikov hydration. Those reagents are going to look very familiar. BH3, and don't forget the 1 and the 2, H2O2, and OH minus. Now, do I have any space? Yeah, I have a little space. So the intermediate in this case looks like this. Right now, in this video, I'm not going to go over this isomerization. You may know already from previous videos that this is called the enol form. And it isomerizes to what's called the keto form. But let's not call it the keto. Let's name this molecule or give the class of molecules. This is an aldehyde. When you have a terminal alkyne, you can choose how to make an aldehyde or a ketone by choosing the appropriate reagents. Now, one last note, let me put it here. There's a special reagent that helps, again, accentuate the regioselectivity, and instead of using BH3, you could use a derivative of BH3, which is called SIA2BH. SIA is a very bulky alkyl group that helps position the oxygen at this end carbon, the less crowded carbon. The details, again, I'm not going to go over right here. All right, we haven't had reagents for these three arrows down here. These are all reductions. And the first one you should be very familiar with, H2PT. So we reduce the triple bond all the way to a single bond. The hard part about this is make sure you can draw the correct number of carbons, and I like to put dots where the original triple bond was. So between these two carbons, and we have two more at the right. We made an alkane in this case, alkane. Now, if you want to make a alkene, if your triple bond is internal, there are two options. You can make a cis alkene or a trans alkene. So this is a cis, this is a cis alkene, and this is a trans alkene. The reagents for this cis alkene synthesis is very similar. I'm going to draw this one also sideways. We are using H2 gas again, and something called Lindlar's catalyst. Lindlar's catalyst, or just Lindlar cat. Now this is one of the few cases where I will allow students to write the name of the reagent instead of the actual chemical. Lindlar's catalyst adds hydrogen on the same side of the triple bond. Hence, you can realize if your two hydrogens are on the same side, then that will automatically make the alkene cis. Before we go to the transalkene, I want to mention that Lindlar's catalyst, or Lindlar's cat, equals palladium, but it's been, you can think of it as it's been modulated so it's not as strong as the regular palladium metal. And it's been modulated with calcium carbonate, CaCO3. It's a weaker version of palladium, so we don't go all the way to the alkane, we stop at the alkene. And the third reduction uses sodium metal. Okay, so not the ion, and sometimes I like to make sure that it's very clear that it's the metal by putting O for neutral. It's not Na+. And it's typically run in ammonia liquid. Okay, don't get that confused with sodium amide, which is up here, strong base. This is the conditions to make the transalkene, sodium metal and liquid ammonia. Okay, I think I could get most of the alkyne reactions on the same screen. Okay, so ultimately, how many reactions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, starting from the alkyne. Some of them go through an intermediate. Okay, I promised that I would show the synthesis of an alkyne. Actually, we do have a synthesis of an alkyne here, from a terminal to an internal, but what if we're starting with not an alkyne, but an alkane? So that part of the roadmap is to the north, right there. And we're going to go from alkane to alkene to alkyne. Actually, that's why I have different colors for the arrows. All the green arrows are formally in the alkyne unit where you're using alkyne as a reagent. Here, these black arrows are going to be converting an alkane all the way to an alkyne. A very classic synthesis. You have Br2 and HV light or HV, which is light, or you could use heat. You all know this as radical halogenation. We can't put a bromine here, and when we're choosing between a secondary and a primary carbon, you put it on the secondary carbon. Then we do elimination. The base I like to use is NaOET to make the alkene. Elimination. So these are review reactions. You probably learned this reaction when you talked about radical reactions, and this one when talking about elimination reactions. This is an alkene reaction, and we're adding Br2 to each alkene, or 1 Br to each carbon of the alkene. And typically I like to use chloroform, and I show chloroform as a solvent. Okay, the last arrow, I believe, in this whole roadmap is right there, and we're converting a dihalide dihalide into an alkyne. We're doing a double elimination. The first elimination is to make the pi bond, but we have two BRs, so the second elimination will make the second pi bond of the triple bond. This is a little bit subtle. Some professors will allow you just to put base. I like my students to know that we'll need 3 equivalents of base. What does that do for us actually? It gets us to the carbon anion, or the triple bond anion. Because if you only have 2 equivalents of base, sure, if everything works perfectly, you'll get the triple bond because those 2 equivalents of base will do 2 beta hydrogen eliminations. But the thing is, once the first alkyne is made, it's going to start deprotonating and using up the base before that base has a chance to do the elimination. So instead of using 2 equivalents, we'll use 3 and make sure that all of the product is a C anion, and then we protonate it to make the neutral alkyne. A little bit subtle, and if you didn't quite follow, don't worry about it. Uh, in in general, you're going to use a lot of base and then protonate the C minus that was here. Okay, one zoom out, and then I'll let you all go. So I do provide a roadmap of the alkyne reactions, but I highly suggest that you make your own roadmap. Maybe you could arrange the cities a little bit better. Maybe you could put your own notes as you go through the lectures, any other notes that you want to add. But for this to stick and for this to have easy recall during an exam, you'll want to draw your own roadmap. You just can't study off of this one here. I don't think the concepts and the reactions and reagents will be sticky enough unless you draw it by hand on your own. But this is a good guide, I think, to making your own roadmap.